Welcome to Lecture 3 of our Probability Theory course. Today we're going to explore one of the most fundamental and powerful tools in probability, the theorem of addition of probabilities of incompatible events. This theorem provides us with a simple yet elegant way to calculate the probability that one of several mutually exclusive events will occur. Understanding this concept is absolutely essential because it forms the foundation for many more advanced topics in probability theory that we'll cover later. Whether we're analyzing the chances of winning a game, predicting outcomes in finance, or solving complex statistical problems, the addition theorem is always close at hand. By the end of this lecture, you'll not only understand the theorem itself, but you'll also be able to apply it confidently to real-world problems. So let's begin our exploration of this fundamental principle, starting with a simple question. If we have two incompatible events with known probabilities, how can we find the probability that either one or the other will occur? Let's start by considering a fundamental question. Suppose we have two events, which we'll call A and B, and we know that these events are incompatible. That means they cannot occur simultaneously in the same trial. For example, when tossing a coin, getting heads and getting tails are incompatible events because you cannot get both on a single toss. Now let's say we know the individual probabilities of these events. The question is, how can we find the probability that either event A occurs or event B occurs? In other words, what is the probability of A plus B, where the plus sign represents the union of these two events? This is not just a theoretical question. In real life, we often face situations where we want to know the probability of one outcome or another, and we need a reliable method to calculate this combined probability. The answer to this question leads us directly to the theorem of addition, which provides a beautifully simple solution to this problem and serves as one of the cornerstones of probability theory. The theorem of addition states that the probability of the occurrence of any one of two incompatible events is equal to the sum of their individual probabilities. We express this mathematically as P of A plus B equals P of A plus P of B. This is remarkably straightforward. When events cannot happen together, the probability that either happens is simply the sum of their separate probabilities. But the power of this theorem doesn't stop there. We also have an important corollary. The probability of the occurrence of any one of several pairwise incompatible events is equal to the sum of the probabilities of all these events. This means that for any number of mutually exclusive events, we simply add their probabilities together. For example, if we have three incompatible events, P of A plus B plus C equals P of A plus P of B plus P of C. This theorem is incredibly useful because it allows us to break down complex probability questions into simpler components, calculate each component separately, and then combine the results through addition. Now let's apply this theorem to a practical example. Imagine a shooter aiming at a target that is divided into three distinct areas. The probability that the shooter hits the first area is 0.45, and the probability of hitting the second area is 0.35. We need to find the probability that the shooter will hit either the first area or the second area with a single shot. This is a perfect application of the addition theorem because the events are incompatible. If the shooter hits the first area, they cannot simultaneously hit the second area, and vice versa. So we simply add the probabilities. 0.45 plus 0.35 equals 0.80. This means there's an 80% chance that the shooter will hit either the first or the second area on any given shot. What's particularly nice about this example is how intuitive it is. If you have a 45% chance of one outcome and a 35% chance of another mutually exclusive outcome, then you have an 80% chance of getting either one. The theorem simply formalizes this intuitive reasoning and gives us confidence in our calculations. Let's consider another example to reinforce our understanding. Suppose we have an urn containing 30 balls, 10 red balls, 5 blue balls, and 15 white balls. We want to find the probability of drawing a colored ball, which means we want either a red ball or a blue ball, since white is not considered a color in this example. The probability of drawing a red ball is 10 out of 30, which simplifies to 1/3. The probability of drawing a blue ball is 5 out of 30, which simplifies to 1/6. These two events are incompatible because drawing a red ball and drawing a blue ball in a single draw are mutually exclusive outcomes. So we apply the addition theorem. 1/3 plus 1/6 equals 2/6 plus 1/6, which is 3/6 or 1/2. This tells us that there's a 50% chance that a randomly drawn ball will be colored. This example is particularly instructive because it shows how we can combine probabilities for different categories of outcomes, as long as those categories don't overlap. The addition theorem is essentially the mathematical foundation for saying either this outcome or that outcome will occur. Now we move on to another important concept related to the addition theorem: the complete group of events. A complete group of events is a set of events such that, in any given trial, at least one of them must occur. In other words, these events cover all possible outcomes. The theorem states that the sum of the probabilities of events that form a complete group is always equal to 1. This makes perfect sense because if these events cover all possible outcomes, then the probability that one of them will occur is 100%, which is represented by the number 1. For example, when rolling a standard die, the events of getting 1, 2, 3, 4, 5, or 6 form a complete group because one of these outcomes must occur. The sum of their probabilities is 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6, which equals 1. This property is incredibly useful because if we know the probabilities of all but one event in a complete group, we can always find the probability of the remaining event by subtracting the sum of the known probabilities from 1. Let's see this concept in action with a concrete example. A consulting point of an institute receives packages with control works from 3 cities, which we'll call A, B, and C. The probability of receiving a package from city A is 0.7, and from city B is 0.2. We need to find the probability that the next package received will come from city C. The key insight here is that these 3 events, receiving a package from city A, from city B, or from city C, form a complete group. The next package must come from one of these 3 cities, so the sum of the probabilities must equal 1. Therefore, we simply add the known probabilities, 0.7 plus 0.2 equals 0.9, and subtract this from 1 to get 0.1. So there's a 10% chance that the next package will come from city C. This example beautifully demonstrates how the complete group theorem can be used to find unknown probabilities when we know the probabilities of all other possible outcomes. It's a practical tool that we encounter frequently in real-world applications. Now let's discuss a special case of complete group events, opposite events. 2 uniquely possible events that form a complete group are called opposite events. In other words, if there are only 2 possible outcomes in a trial and they are mutually exclusive, they are considered opposite events. For example, when shooting at a target, getting a hit and getting a miss are opposite events because there are only 2 outcomes and they cannot both occur. Similarly, when randomly selecting a detail from a box, the events a standard detail has appeared and a non-standard detail has appeared are opposite. In probability notation, if we denote one of these events as A, the opposite event is denoted by A with a bar over it, which we read as not A. This notation is extremely useful because it allows us to refer to the complement of an event concisely. Opposite events are fundamental in probability because they provide a way to calculate the probability of an event's complement, which is often easier than calculating the probability of the event itself. Just as with any complete group of events, the sum of the probabilities of opposite events is always equal to 1. This gives us the important relationship that P of A plus P of the complement of A equals 1. From this, we can derive an equally important formula. The probability of the complement of A equals 1 minus the probability of A. This formula is incredibly useful because sometimes it's easier to calculate the probability of an event not happening than it is to calculate the probability of the event happening. Let's look at a simple example. Suppose the probability that a day will be rainy is 0.7. We want to find the probability that the day will be clear. The events, the day is rainy and the day is clear, are opposite because there are only 2 possibilities and they cannot both occur. Therefore, the probability of a clear day is simply 1 minus 0.7, which equals 0.3. This is a 30% chance of a clear day. This relationship between opposite events is one of the most frequently used tools in probability because it provides an elegant way to handle situations where the complement is easier to analyze than the original event. Now we move beyond the addition theorem to introduce the concept of conditional probability. Conditional probability is a fundamental concept that allows us to update our probability assessments based on new information. Specifically, the conditional probability of an event B given that event A has already occurred is denoted as P subscript A of B and is calculated as the probability of the joint occurrence of A and B divided by the probability of A, provided that P of A is greater than 0. This formula makes intuitive sense because when we condition on event A occurring, we're essentially restricting our attention to the subset of outcomes where A has happened. The conditional probability tells us, within that restricted space, what the probability of B is. Conditional probability is incredibly important in real-world applications because we rarely analyze events in isolation. Instead, we often have information about certain occurrences that allows us to refine our probability estimates. This concept forms the foundation for Bayesian analysis and many other advanced statistical methods. Building on conditional probability, we now arrive at the theorem of multiplication of probabilities. This theorem states that the probability of the joint occurrence of two events is equal to the product of the probability of one event and the conditional probability of the other event, given that the first event has already occurred. Mathematically, we write this as P of AB equals P of A times P subscript A of B. This theorem provides a powerful method for calculating the probability that two or more events will happen together, which is often crucial in real-world applications. For example, if we want to know the probability of drawing two specific cards in sequence from a deck, we would use this multiplication theorem. The key insight is that when events are not independent, we need to account for how the occurrence of one event changes the probability of the other event. This is what the conditional probability captures, and the multiplication theorem gives us a systematic way to combine these probabilities to find the joint probability. The multiplication theorem can be extended to more than two events through a valuable corollary. The probability of the joint occurrence of several events is equal to the product of the probability of one event and the conditional probabilities of all the remaining events, with each conditional probability calculated assuming that all preceding events have already occurred. The general formula is P of A 1 times A 2 times A 3, continuing up to A subscript n equals P of A 1 times P subscript A1 of A 2 times P subscript A1 A2 of A3, continuing through to the final conditional probability. For three events, this simplifies to P of A, B, C equals P of A times P subscript A of B times P subscript A, B of C. This extended theorem is extremely useful when we have sequential processes where outcomes depend on what happened before. For example, in quality control, if we're sampling items from a production line without replacement, the probability of each subsequent item being defective changes based on what we've already observed. This corollary gives us the mathematical framework to handle such situations precisely. Let's work through a complete example to see the multiplication theorem in action. We have an urn containing 12 balls, 5 white, 4 black, and 3 blue. We're going to draw 3 balls without replacement, meaning we don't put them back after each draw. We want to find the probability that the first ball drawn is white, the second ball is black, and the third ball is blue. This is a classic application of the multiplication theorem. First, the probability that a white ball appears at the first trial is 5 out of 12. Now, assuming that a white ball has already been drawn, there are only 11 balls left, of which 4 are black, so the conditional probability of drawing a black ball at the second trial is 4 out of 11. Finally, assuming that a white and a black ball have been drawn, there are only 10 balls left, of which 3 are blue, so the conditional probability of drawing a blue ball at the third trial is 3 out of 10. Multiplying these together, we get 5 over 12 times, 4 over 11 times 3 over 10, which equals 60 over 1,320, simplifying to 1 over 22. So there's approximately a 4.5% chance that this exact sequence will occur. This example beautifully demonstrates how the multiplication theorem handles sequential events, where the probabilities change at each step.